Paper 2 Calculations. In part 1 of this series, you would have gone through transformer calculations. In this part of the series, we will look at calculating floor area, generator calculations, and calculating efficiency. These are the key calculation items that will enable you to be successful on the BGCSE Paper 2 examination. Floor area calculations. Calculating floor power. Now, the National Electrical Code, NEC, states that there must be 3 voltage amperes of power provided for every square foot of living space. Let's keep that in mind. Now, how do we calculate living space? Let's look at this illustration here of a floor plan of a 2-bedroom apartment. Just labeling a few areas, you will see here a carport, 2 bedrooms, living room, kitchen, and probably a bathroom would be here. This space could be a washroom. Now, in order to calculate the total floor area of this building, we will have to know what is the width and the length. That's the overall floor area. However, the living space is the space where most of the current or all of the current or the power will be used at most times. So the living space will be the total floor area minus or take away the area of the carport. So let's put some figures in and let's begin our calculations. To calculate the total floor area in square feet, first of all, the overall measurements using a scaled ruler, we will be able to find the length to be 26 feet 0 inches and the width to be 40 feet 0 inches. In many cases, it doesn't matter which one of these are designated length or width, because we know area is length times width. So we will begin by calculating the area of the overall building. Now, the overall floor area would be taking these measurements here and multiplying them together. So the length times the width would give us 26 feet times 40 feet, which gives us 1,040 square feet. Now, calculating the area of the carport, we will see that we are using these measurements here, 12 feet and 8 feet. Length times width, 12 feet times 8 feet gives us 96 square feet. Hence, the total living space will now be equal to 1,040 square feet minus 96 square feet, which now gives us 944 square feet. This now takes us to calculating the floor power. Now, as you would remember, the National Electric Code states that there must be 3 voltage amperes of power provided for every square foot in a living space. Therefore, we will take the living space and we will multiply it by 3 voltage amperes. This gives us 2,832 watts, or it can be represented as 2,832 voltage amperes. Remember, power is equal to voltage times current. Therefore, voltage amperes is the same as watts. Now, this is a key point. Whenever you're answering a question of this caliber, please remember that you must place all the devices in the floor area using the principles given in the booklet. You will place on each wall a socket and a switch to control the lights. Just please remember to review that. Generator calculations. A generator is a machine that converts mechanical energy into electrical energy. Therefore, we need to understand how it operates and we need to calculate the amount of power and the amount of voltage and the amount of current that a generator will be able to transmit and supply to an electrical service. Here are some key formulas, or the key formula for calculating these values in a generator: power, current, and voltage, or our power triangle, which is pi. We also need to be fully aware of our American wire gauge, which will help us to understand what conductor size will be used. For example, for a conductor size of 14 AWG, what is the overcurrent protection for that? And that would be 15 amperes. So in this exercise, we will seek to use the values given on the generator here to find out the amount of current on each circuit A, B, and C. And then finding that current that is used on A, B, and C, we will be able to determine what conductor size we will be using, and also the overcurrent protection that will be able to transmit this current safely along the circuit. So here we see we have a 50 kilowatt generator that supplies 250 volts as well. On circuit A, we have 300 watts of power. 3000, watts of power. Circuit B, we have 4000 watts of power, and circuit C, we have 900 watts of power. Now, let's calculate the amount of current that is supplied on circuit A given 3000 watts at 250 volts. So, using our formula, current I is equal to power P divided by voltage E. So we will take this 3000 watts, we will divide it by 250 volts. We will get 12 amperes. This 12 amperes now, we will apply this 12 amperes to our American wire gauge. Applying it to our American wire gauge, we will realize that we cannot go an ampere lower. We must go an ampere higher. And the closest amperes we have to use is 15 ampere for the overcurrent protection. And a 15 ampere overcurrent protection gives us a wire size of 14 AWG. So we now move on to circuit B. Circuit B has here 4000 watts. Using the same formula, I is equal to P over E. We have 4000 watts divided by 250 volts, which gives us 16 amperes. For 16 amperes, we must go higher again, and we get 20 amperes as our overcurrent protection device, which gives us our wire size of 12 AWG. And onto circuit C, which has 9000 watts. I is equal to P over E, which is equal to 9000 divided by 250. 9000 divided by 250 gives us 36 amperes. 36 amperes of overcurrent protection is 40 amps, and our wire size is 8 AWG. Let us keep in mind, we must know our American wire gauge overcurrent protection and wire sizes. Obviously, the higher the current, the lower the AWG number. Let's keep that in mind. And let's keep our key formula, which is pi, power over current and voltage. If asked to calculate the efficiency of an alternator or a generator, or even of a transformer, efficiency is equal to the ratio of power output divided by power input. An alternator is an AC generator, right? Suppose this alternator has an input of 14.92 watts of power. It has a terminal voltage of 240 volts. And this 240 volts is supplying a load which has 15 amps applied to it. What would be the efficiency of this alternator? Firstly, we have here given 14.92 which is our input power, we need to calculate output power. Output power now would be equal to I times E. So we have been given 50 amperes as our supply or load amperes and 240 volts as our voltage. Multiplying them, we get 12,000 watts. Converting that watts to kilowatts, we get 12 by, of course, dividing by 1,000. So we now have our output power. So efficiency is equal to power output over power input, which would be 12 kilowatts over 14.92 kilowatts times 100, because we are going to find the percentage. This gives us 0.804 times 100. We are rounding that off to now 80%. So this alternator would be 80% efficient. Now that concludes paper 2 calculations. It's quite simple. Let's put our heads together and we will be ready for this exam.